estuvo un tiempito en Calar Alto, donde nos coincidimos temporalmente.
Sebastián was my boss.
Y creo que él se acuerda profundamente de este periodo. Y bueno, él entiende perfectamente español, ¿eh? Y en la charla seguramente la dará en inglés, pero sabe español, sabe francés, sabe ruso. Este hombre es la leche. Bueno, estuvo haciendo un postdoc en Marsella, después estuvo en París y en Leiden, en la ESA. En el 2010 pues, se volvió a Potsdam, a la IP, donde ya no coincidimos, pues ya me había ido. Y desde el 2015 pues es investigador, lo que sería el equivalente al investigador titular allí en Postdam. Y aparte de eso, pues tiene bastante experiencia en instrumentación, es el Project Scientist de Formox, que es un instrumento que irá a algún telescopio algún día en la ESO, ¿no? Cuando los ingenieros lo terminen. Y por supuesto es el Project Scientist de CALIFA y su experiencia científica mayor es en el análisis de poblaciones estelares en galaxias. Es un experto reconocido a nivel mundial, tiene varios reviews, el del 2011 es fundamental si alguien quiere trabajar en esto. Y bueno, pues nos va a hablar de the velocity function and enrichment history of galaxies. So now I let to him, okay?
Thank you, Sebastian. Thank you, everyone, for coming here and listening to my talk. Sebastian was very kind with my Spanish. I can say a few words, but not much more. I will talk today about the velocity function and the enrichment histories of galaxies, and I will really start out with the enrichment histories, and that will be the main part of the talk. But at the end, I want to show a result on the velocity function that we recently obtained, and I think is very nice and fundamental. Anyway, I started with the enrichment histories, or chemical evolution of galaxies and the results that we had recently. Just to recap, in particular for those of you who might be students, how does the matter cycle in galaxies work? Well, you have a galaxy that's here on the right, and in that galaxy you have typically stars, in particular have gas, and that gas, as you see on the left, tends to be in clouds, which then condense, make stars, and then some of those stars explode in some way or another and contribute metals to the gas that makes the next generation of stars. And that matter cycle is what fundamentally causes what many people call chemical evolution, so the enrichment of metals over cosmic time. And as you know, we wouldn't be here. My hand at some time was 10 to the 6th degrees hot, which is a bit weird to think of. This is the closed box model if, of course, stuff happens. So you have gas accretion, you have accretion of satellites or small or large galaxies, and winds, and they change the fundamental picture of how the easiest way of chemical evolution would go. But still, as we know, galaxies partially can be approximated by closed boxes. So what kind of stars contribute to the enrichment of the interstellar medium of the gas? First, there are supernovae type 2, which are massive stars that explode on short timescales, less than 10 million years. And they produce a large number of elements, including iron and alpha. And you'll hear the words alpha and iron a lot throughout the talk. And in particular, they have a pattern, which is that the abundance of alpha elements is higher than that of the sun. And so the sign here, alpha over iron, that is to the right, would be 0 for the sun, and it's 0.4, around 0.4, typically for type 2 supernovae. This is the first thing that happens to the, after you make some stars, this is the first kind of stars that explode. The second kind of stars are the supernovae 1A, which explode on timescales larger than 30 million years. And they produce essentially iron, a lot of iron. And so over time, iron over H will be raised and alpha over iron will be lowered as you have more supernovae 1A for the next generation of stars. AGB stars and other stars that make winds also contribute to the enrichment of the interstellar medium, but on different time scales, and they produce their characteristic elements are harder to measure, and they won't matter that much for this talk. So if you look at a closed box model in 3 parameters, which would be iron over H, which some people call metallicity, alpha over iron, which is the overabundance of alpha elements as compared to the sun, and a parameter that I would call H from now on, which really is look-back time. Then if you looked at stars in a galaxy, they would lie along those lines. So, so if you, let's take the upper left one to start out with. At the right is the Big Bang, and that galaxy started forming stars, and with time, iron over H increased. At the same time, because in the beginning you had a lot of supernovae type 2, and then supernovae 1A came in later on, alpha of iron drops slowly. First it drops quickly, and then it drops more slowly. And a very characteristic plot that is being done a lot in the Milky Way in particular is the lower left one, where you directly compare iron and alpha, where you have where those two knees that you see in the other two plots actually translate into a knee. So in the beginning, iron gets enriched by supernovae type 2, and at the moment that the iron enrichment is dominated by supernovae 1A is when that knee appears, and you actually go down in alpha over iron. And that knee is a classical diagnostic in the Milky Way. So this is a plot for Milky Way stars from Fuhrman et al. This is one of the very, very few samples where people of the Milky Way actually have thought about the word volume complete. Anyway, so what happens here is that there is, again, the same knee. So you see that there's a plateau at 0.4, and then things start to drop. There actually are two knees in this plot, one for the thick disk and one for the thin disk, but this is a detail that doesn't matter that much. The point is that this plot shows single stars in the Milky Way. And such a plot has never been made outside of the local group. Why? Because we can't observe single stars outside of the local group very easily. So what kind of galaxies would we see outside of the local group? Well, Milky Way galaxies, but we also see a lot of galaxies that are more massive, early type galaxies that are not like the Milky Way because they have stopped forming stars, and therefore we call them early type galaxies. Now, it so happens, either good or bad as you want, is that the chemical evolution of early type galaxies is going to be more complicated than that of the Milky Way. The Milky Way disk is going to be much closer to a closed box. Then an early type galaxy is going to be much more affected by merging, which is what makes the transition from a disk to a puffed up system, right? This is a plot from Thorsten Knapp's work in 2009, where he looks at the mass growth. So again, time goes from the right to the left, and the black squares are the total mass growth of an early type galaxy. And he divides that into two different kinds of mass growth, one of them being the in situ formed stars, so stars from the gas that is in the galaxy, and the other one being stars that were accreted. So there's two fundamentally different components in early type galaxies. This is the in situ formed stars and the accreted stars. And as you see, there's a transition at very roughly 9 to 10 gigayears ago, where in the old phase, most stars were formed in situ, and then in the younger or intermediate age phase, most stars that contribute to the growth of the galaxy are actually accreted stars. So what does that do for your chemical evolution? Well, you can try to relate your parameters that you can possibly measure to things. So the first one is that because you're going to measure average properties, the alpha over iron is going to be related to the speed of the initial star formation. How many of the stars were formed very early on before supernovae 1A could contribute, and therefore, and then the higher the alpha over iron, the higher the speed of the initial star formation event. And again, for the in situ formed stars, iron over H must increase with time, just as in the cartoon for the Milky Way. For the accreted stars, this is unlikely to be the case. Actually, most of the accreted stars will come from dwarf galaxies. Therefore, iron over H will drop with age, which is not expected in a closed box chemical evolution model. So the first quarter of the talk, where I'm starting to introduce our results, will be, can we look at that knee in early type galaxies? Because that would, as I just showed you, would help us diagnose how mass growth in early type galaxies happens. This is work with the collaborators mentioned down there. And what did we do? Well, we take spectra of galaxies, and we fit them with stellar population models. I don't want to introduce stellar population model in much detail here, but essentially what's happening is that we have a model that tries to model all of the features in the black line, which is the observed spectrum, and then we have a red line, which is the fitted spectrum, which is the best fitting stellar population model that we can have, and that allows us to derive the parameters up there, which is the age, the iron, and the alpha, on average, for all of the stars in the galaxy. Okay, so you get 3 parameters per galaxy. Down there is the chi-square minimization function, and there's a whole lot of technical detail involved, which I will not talk about right now. What have we done in terms of sample? We've done something that many people nowadays do. We go to Sloan, actually DR7, selected spectra with good signal to noise. We selected them to be early type galaxies, so have no emission lines, and this is one example of a real fit that we get. So again, in the upper panels, there's a black line and a red line, and the red line is the fit, and this is supposed to convince you that the fit is excellent. And down there, you can see that although we selected for absence of emission lines based on previous work, our fit is so good that we now actually see the O3 and H beta emission line. And down up to the right is a mass histogram, so it's about 10 to the 11 solar mass galaxies, more massive than the Milky Way. What's new in this work? Because this kind of work has been done previously. First, we have improved stellar population models that allow us to determine those parameters from the full spectrum. And the second thing that our approach allows us to do is to rigorously treat degeneracy errors. I will not talk much about this today, but if you follow through with the paper, then you will find a whole long discussion about justifying what we can do, what I will try to show you that we can do. So the first thing to do is to recover what is known. What is known is that the alpha over iron abundances of early type galaxies depend on mass, either measured by its velocity dispersion or the stellar mass of the galaxies. And you can see that there are the usual trends. So the more massive galaxies have a higher alpha over iron abundance ratio, which is typically interpreted as them having formed faster, which is in accordance with their old ages. And the right column is a bit new because ages have not been measured to that precision before. And you can see that we're actually recovering some of the trends that I alluded in the cartoon, and I will come back to that later. Now, what's really new in this paper is that we decided that we could not go for 3, but for 6 parameters per galaxy by separating the star formation history into 2. We chose 9 gigayears or 9.5 gigayears, motivated by the NAP plot that I just showed, and we said all stars older than 9.5 gigayears have an average iron and average alpha, and all stars younger than that have an average iron and average alpha. And you see the subscript I and O here. So you end up with 6 parameters per galaxy. Okay, so you have an age of the old stars, you have an age of the intermediate age, etc., etc. And now what you can do, you can make the same plot that we made before, which is iron over H versus alpha over iron, and you can try to place the early type galaxies. Let me walk you through what's in this plot. The line is the thick disk of the Milky Way, very similar to what I showed before in the Fuhrmann plot. The stars are the bulge of the Milky Way from the work by Bensby et al. So you can already see that the knee that we alluded to earlier is shifted to higher iron values. And now the red and the blue dots are from our work. So the red dots are the old stars, and the blue dots are the intermediate age stars in the early type galaxies. So now every galaxy gets 2 dots in this diagram. And you immediately see that a line like for the bulge and the thick disk does not work for the majority of early type galaxies. Okay, so there is no knee. Early type galaxies are not closed boxes in terms of chemical evolution. We can actually separate them into 2 classes. Some actually are consistent with the knee. So the iron over H of the intermediate age stars is higher than that of the old stars. Those are the ones we call self-enriched. And there are the other ones where the iron over H of the intermediate age stars is much lower than that of the old stars, and those we think are dominated by accretion. And within our sample, which is admittedly maybe not the cleanest selection, but still it's pretty large, 80 to 90% are accretion dominated, and only 10% are consistent with a self-enrichment scenario. So in this work, what we show is that this is not new. Okay, we know that massive early type galaxies have been affected by accretion, but we show that we can diagnose it by chemical arguments, by chemical measurements. And we can give a fraction of early type galaxies. And now comes a plot that I really made as a fun thing 1 week ago, so don't take it too seriously. But actually, you can look at the iron over H of the knee. The iron over H of the knee is something like, as I said, the speed of the initial event of star formation. And if you look at the right, the plot down right there, This plots the knee for satellite galaxies of the Milky Way. And you can extrapolate that by several orders of magnitude, and you end up by the early-type galaxies. This is really, if this is really, I made it a week ago, and I need to think about it a bit more, but if this is true, then we really have, chemical evolution. The speed of the initial event of star formation is dependent on today's mass of the galaxies. That's really fascinating. But that's really very much in preparation. Conclusion 1, accretion histories of early-type galaxies are visible in the chemical signatures of their stars. Now, let's come back to the plot of H versus off over iron. And this is a paper that is in preparation, and I'm giving you the list of collaborators is a bit different, and the title is a bit different. So let's come back to the cartoon. We said we wanted to look this time at the, we looked before at the lower left, and now let's look at the lower right plot, H versus off over iron. So this is, I've argued in the beginning, this is fundamental, right? I've said, well, this is expected. The problem has been that age is hard to do. The age of stellar populations, of single stars is very, very hard, and of stellar populations in general is hard to do, to get right in a systematic and absolute way. So in the literature, people have been looking for relations between the mass and the off over iron, the sigma, the iron of H, etc., and there are many more relations. But people have tended not to look at the H off over iron. But all of these should be secondary consequences of the relation between H and off over iron. So I've gone through the literature, and I've found a few papers where something like that has been published. The upper left here, you see, there's some kind of a magnesium versus age plot. Then this is from Graves, also from Sloan, but this is, tens of thousands of spectra stacked over each other, but still you can see that magnesium over iron versus age follows some kind of a trend. And then people in the Sauron survey have also been looking at similar things, but this is, very limited sample sizes, and they haven't been making much of it. Now we decided to make much of it, and we said, okay, this is exactly what we expected from basic chemical evolution arguments. And this is a bit surprising, okay, because I just said chemical evolution does not work for early-type galaxies, but it works for these plots. So let's keep that in mind. And it's not only, that it's one thing, it's really a double thing, as you can see, as a generic prediction of chemical evolution models. Now, because this is generic prediction, I thought, okay, let's just look at the stars of the Milky Way as well. So upper left is, again, massive early-type galaxies, averaged over the entire galaxy, H versus off over iron. Upper right are single stars around the sun. This is weird. This is massive 10 to the 11 solar mass galaxies that have stopped forming stars several gigayears ago, follow exactly the same plot as single stars in a lowish mass disk galaxy that is forming stars to today. And the lower two panels show models. The left one is for early-type galaxies, the right one is for stars in the Milky Way. And you can see, so the solid line is really the reference line that we derive for the early-type galaxies, that all of these have very, very similar things. So we're comparing apples and oranges. And they're similar. They're all round. Is that same true for H versus iron of H? No, it's not. Okay? The iron enrichment of the systems is very different, which is expected because their star formation histories are different. So if it doesn't depend on star formation history, then what determines this? What else can we maybe learn from this? And this plot is trying to show what we can learn. So again, the data in the upper left, and now we have 3 different models, and you see they have funny codes. And the codes are different delay time distributions of supernovae 1A. I told you that the enrichment with iron, and in particular the way that alpha over iron decreases with time, depends on supernovae 1A. And so we can put in different delay time distributions. So this is the number of supernova 1A that occur after a starburst event. And we can test which one reproduces our data. We put in 3, the 3 ones that are really, the ones that people think. And as you see, they can be quite different. These delay time distributions have been derived by supernovae 1A observations at different redshifts, and people have been looking at stellar masses and star formation rates, and they have done complicated statistics to try and get their best estimate of the delay time distribution. There are 3. One is bimodal. This is the solid line here. One is a single Gaussian. This is the dotted line. And the other one is the power law. This is the dashed line. And now we come back to these, and you see only one of them fits. It's the power law one. The other 2 do not fit. Okay. So without ever measuring a single supernova 1A explode, we have a way of constraining the daytime distribution of supernovae 1A in a very good way. And we think that is a fundamental result that we hope to publish over the next weeks. So I'll come up with these conclusions so you don't have to read them at the end. So there's a universal age of relation which helps us constrain the delay time distribution of supernovae 1a. Good. Now, as Sebastian said, I'm the project scientist of CALIFA, so I have to show you some CALIFA results. Actually, there's a good reason to do that, because okay. I'll do my 2 slides about CALIFA. Most of you will know them, but just in case anyone is in the room who has not ever heard of CALIFA. What is CALIFA? CALIFA is a survey of local galaxies, very low redshifts. We have observed 600 galaxies of all Hubble types out of 3 effective radii on average, with a full optical wavelength coverage and a very well understood sample selection, which is one of the defining criteria of the survey. And we get 900 independent spectra per galaxy with a very good signal to noise, which again is pretty unique. We have released the data in 2014, and this is the keynote effects I promised you, Sebastian. And we will release all of our cubes that are useful for science in April, and 2 weeks from now. And this is the figure that shows how nice CALIFA is, because this shows just 6 of the many, many, many different kinds of physical properties we can get for the galaxies, and we don't only get them for as an integrated value, but we really get maps for the galaxies. And but because I think that most of you know, I will not go into the details of this figure right now. So let's come back to why do we now need to look at the chemical enrichment in a spatially resolved way? The reason is that accreted stars tend to be deposited in the outskirts of early type galaxies. This is what all simulations predict. Okay. Gas, on the other hand, accreted gas would typically go to the center and make stars there. So we're expecting that the gradients in the chemical properties of early type galaxies should help us understand their evolution. These projects are still underway, so I won't give you quite as clear messages, but I will still try to show you what we've done. So this was a master thesis by my student, Maria Haupt. She looked at 8 galaxies that she selected to be nice. Okay, those are just the nicest early type galaxies that were observed at the time that she was starting her master thesis. And then what she did is that she defined elliptical annuli in which she binned all of the spectra to get high signal to noise spectra and to make a radial trend for the abundances. And her biggest surprise, and I was also interested, was that the word gradient by itself means something that is kind of linear, right? A gradient is a slope, okay? This is what you give. But there is no way that a single number can capture either that behavior or this behavior or that behavior. Okay, there is no. The radial dependence of physical properties in early type galaxies is not a single gradient. And that is important. I think this is something we need to realize and factor into everything we do. Because, and I will do the same, people tend to compare, for example, simulation with data by plotting slopes. Now, this is wrong. This is a wrong way to do. This is all work in preparation. Nevertheless, we have one main thing that came out of what we did, and that was that our gradients do not completely agree with everybody else's gradients. Everybody else's H gradients are flat, and our H gradients are actually negative, which means that the galaxies are older in their center than they are in the outskirts. On the other hand, our metallicity gradients are much flatter than everybody else's, and they have negative metallicity gradients. So the metallicities in the outskirts of the early type galaxies are lower than in the centers. The exact same comparison is true for simulations, because what simulators do is they reproduce the data. So the data that was available showed those gradients, so they reproduced them. Whether we're right or not, this is why I put the in preparation flag. I think we're right, because this is exactly the same method that I showed before, and we have tested it to death. But, okay, we are not in agreement with the literature. Okay, so point 1. Point 2 is, this was for early type galaxies. So now, what can we learn about disks? Okay. We know that elliptical galaxies do not follow the closed box model. The Milky Way disk does. It's not a closed box, okay, but it's, for the purposes of this talk, it's very similar. So can we look at other disks? Can we look at samples of disks instead of just looking at the disk of the Milky Way? Well, the problem is that measuring alpha over iron is only really possible for old stellar populations. For young stellar populations, the absorption lines get weaker, and then it becomes much more difficult to get a good estimate of alpha over iron. So what we did, we went for the lenticular galaxies in CALIFA, and we did the same exercise as we did before for the elliptical galaxies, which means that we radially binned the spectra, and we defined the disk region as being the part of the galaxy that rotates, and the bulge region as being the part of the galaxy that is velocity dispersion dominated. We also did surface brightness fits, and we, if you take the bulge as being what is above the exponential, then again, we defined two radii in this way, and everything that was inside both radii was called the bulge. Everything that is outside both radii is called the disk, and everything that's in between is called the transition region. So we have 3 regions for every one of our galaxies. So now let's look at the H versus alpha of iron plot for those regions. And so now every dot here is one of the radial zones in one of the 40 S0 galaxies. Okay, so it's a bit of a mix, and we still need to improve on our presentation. But the fundamental message is the red line here is the line I showed you before from the early type galaxies from Sloan, and the fundamental message is here that bulges lie on that relation. Great. The transition regions show a bit more scatter and maybe lie on that relation. The disk regions, some of them lie on the relation, but there are some that really are not where we wanted them to be, okay? Because those are young, alpha-rich regions and the disks of lenticular galaxies. And this is not allowed by chemical evolution. Wow. How can you do this? For those of you who like Star Wars, there's this flying thing, and he said, how can you do this? Well, first thing we did, of course, okay. Probably we did something wrong, okay? So let's find a way to show that this is really in the data. Okay. This is the residuum, the residua from our fits to the CALIFA data. And the black line, so this is the model minus the data, or the data minus model, doesn't really matter. The black line is what we find for everything that lies on the relation, okay? So these are the normal regions. The red line is the residuum for the young alpha-rich regions when we just fit them normally and get a high alpha over iron ratio. The green line is what we get when we fit those same regions, but we force alpha iron to be 0, which is what we had expected. And you can clearly see that the magnesium B and the iron features are not fitted in this case, okay? So our data require these regions to be young and alpha-rich. There's no way around this. And actually, if you look at the Milky Way again, then maybe this is not so crazy, because just last year, there have been 2 papers, and this is just one of them, showing that actually also the Milky Way contains young alpha-rich stars in the inner disk. Now, those are single stars, okay? And they're not the majority of stars in the Milky Way. And in our case, the young alpha-rich stars dominate the light of the lenticular galaxies, so it's still a bit different. So we're exploring, we're trying to find out what's going on. And one of the things that we found, the most convincing thing that we found right now is if we split the disk regions by surface brightness, then we find that it's not so much the disk, it's really low surface brightness regions that are up there at the young alpha-rich region. Now that makes us just a bit more comfortable, because that means we don't need quite as many of those young alpha-rich stars, point 1. Point 2, there is you can invent explanations now, and I won't, I haven't dared to put them on a slide so that you can read them, so I will just talk about them. So there are different explanations you can come up with. The 2 that I currently think we should explore are, the first one is maybe this is just very, very bursty star formation at the outskirts of disk galaxies, okay? If you have a very bursty star formation, what happens is that you form a lot of the mass that is locally available within a very short time, so maybe you decouple from the general chemical evolution. The kind of masses that need to be formed are still uncomfortably high, and you still uncomfortably not see those kind of galaxies in the local universe, okay? Because if these S0 galaxies had that behavior, maybe you would expect such very strong bursts in the outskirts of galaxies to still happen in the local universe. There's no literature on this. The other option that we have is that actually those are accreted stars. What do I mean by this? We know that very low mass galaxies are very bursty in their star formation. And we know from the work by Abadi et al. And others that when you accrete a satellite on a disk galaxy, the stars get deposited in the disk. And so the prediction would be that because the very low mass galaxies are so bursty, they might be alpha enriched. Now, no one has ever been able to measure this because, as I told you before, it's very hard to measure alpha enrichment for young stellar population, which is the case for low-mass galaxies. So maybe we're onto something very interesting here. Maybe it's all wrong, but maybe onto something interesting. The last point is, as I told you about the velocity function, and we're now going to completely switch topic. So if you had questions or anything to the other topic, maybe either you want to ask them right now or after the talk, but keep them in mind. So the CALIFA survey is, of course, also great because you can do kinematics of galaxies. And I will just quickly walk you through what we did here. We thought we're going to look at the relation between the luminosity and the circular velocity of galaxies, which is also called the Tully-Fisher relation, from the CALIFA survey. And first we thought, okay, we're going to do this because we can, and in the end it turned out to be very interesting. What is the Tully-Fisher relation? The Tully-Fisher relation in this classical paper from 27 is a low scatter relation between the luminosity and the circular velocity of galaxies. And you can see that it seems to be relatively independent of galaxy type, but it can be well defined only for nicely behaved disk galaxies. You have to be a disk galaxy that rotates very nicely. You have to have gas. You're not allowed to have a merger, et cetera, et cetera. Well, the Tully-Fisher relation was invented by Tully and Fisher to measure distances, because of course when you know the circular velocity and you know its intrinsic luminosity, you know the apparent luminosity, you can get the distance. So that's what Ben Tully still does, and it's very interesting work. But the Tully-Fisher relation has also become a way for simulators to make sure that the galaxies are somehow realistic. So what people do is they have an observed relation. This is the blue squares in this paper from Christensen et al. And there are simulations, which is the red dots, and they put them on the relation. Now, on the relation is a very fuzzy word, because the sample that I showed before and also the McGuff sample are pruned. This is not all galaxies. This is, they've gone through catalogs of galaxies. Out of 1,000 galaxies, they will select 100 for targeting because they're nicely behaved disk, they have a nice blah, 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 they're nice, okay? And then you get a low scatter Tully-Fisher relation. But this is not what a simulator does. A simulator simulates all galaxies, and therefore they should put their galaxies onto something that is more general. And what is more general? It's a distribution function. A distribution function is the number of galaxies per volume, megaparsec cube, per bin in some property. And so in this case, this would be a two-dimensional distribution function. Now, the nice thing about CALIFA is that we can do distribution function. And we showed that in our 2014 paper, where we compared the luminosity function that we obtained from the CALIFA sample, which is the red dots here, to the reference Sloan luminosity function, which is the blue line. And the idea was not to remeasure the luminosity function. The idea was to show that our selection effects are well understood, and therefore we can compute distribution functions. So if we can compute distribution functions, okay, this is a bit more blurb on exactly what we do. So there's a completeness limit. We calculate this completeness limit is, and some people still ask me. I know this is preaching to people who already know, but some people ask me about the diameter selection. How does it affect us, and etc. There is no effect. We're not affected by the diameter selection. So now what we decided to do, we decided to compute the two-dimensional distribution function in the luminosity circular velocity plane from the CALIFA galaxy. So first you have to measure the rotation speed or the circular velocity. The left is a velocity field from one of the CALIFA galaxies as an example, and to the right you see how we measure the circular velocity. So there is a rotation curve, so the dependence of rotation velocity on radius, and then you can see that it flattens out at a certain level, and depending on exactly how you define your circular velocity observationally, you use either 2.2 scale lengths of the disk, or you use 80% of the total light. It comes out to be very, very, very comparable. The luminosities we measure from the SDSS imaging that is available for all of our CALIFA galaxies. Then we do some sanity checks. We make sure that we're not completely off. To the left, we show the circular velocity versus absolute magnitude of the CALIFA galaxy, which is the red dots, versus those of the Courteau sample, which is the open circles, and you can see that there is they both lie in the same region of the diagram. To the right, we show the circular velocity versus the gas velocity. Why do we do that? Because we're working with this stellar velocity. We're working with the stellar velocity because that allows us to include essentially all galaxies, but for a few that are completely dispersion dominated. But all the others we can include, which allows us to compute distribution functions. If we took only the gas, we could not compute a distribution function because we would be missing a large fraction of galaxies. And so it's very important that we're doing this from a stellar perspective. So, check, check. Works well.
Excuse me, are you
Yeah.
putting here every kind of galaxy?
Yes. We're putting everything that is lenticular is in here as well. And that will become very important at the end. Only the really dispersion-dominated, elliptical, big things, there it's very difficult to do. We do a small correction for things like, dispersion support and this kind of stuff that is based on the literature, but essentially we're measuring rotation velocities based on the stars. To the left, you see again circular velocity versus absolute magnitude, and to the left you see the sample number densities. So the dots are the actual galaxies, and the blue haze is a kernel density estimator that just says, how many galaxies are in this part of the diagram, and the light blue stuff is we're not complete. To the right, you see actual space densities. So now this is a plot that has the units of number of galaxies per megaparsec cube. And you can see that things shift as expected, okay? So you're dominated by lower mass galaxies, and actually what happens is that the slope changes very little, okay? We're not so interested in the slope because this is not the main goal of the paper. We quote it in the paper, and the slope changes very little. Now, for me, the most interesting part of the work was when we went ahead and did the marginal distributions of the Tully-Fisher relation, okay? So the relation I just showed you is the bivariate distribution function, and you can collapse it to one side, and then you get the luminosity function. We knew that. You can collapse it to the other side, and then you get the velocity function. The velocity function is the number of galaxies with a certain circular velocity per megaparsec cube. And the velocity function has an advantage of the luminosity function, which is that the luminosity function, you try to measure something like the mass of the galaxy, but it's modulated by a lot of stuff. It's modulated by dust, by the stellar populations, by the star formation. It's modulated by a lot of stuff. The velocity function is modulated by nothing. It's a measure of the rotation speed of a test particle. So you can compare it directly to simulations. And that's what we do here. First, let me explain exactly what we do. So the red points are the velocity function from the CALIFA data, and the blue is a published velocity function from the HIPASS survey, which is gas-rich galaxies. And the point now, coming back to what we said before, is that CALIFA extends that to higher circular velocities. You see that the HIPASS velocity function drops at high masses, which is expected because there is no gas in high-mass galaxies. And now we can extend that to higher masses. And so we have a validity range between 70 and 350 kilometers per second for our velocity function. Measured, and now you can put in the velocity function you get from the Millennium or the Bolshoi simulations. Those lines are thanks to Darren Croton, and what you see is that those get it wrong. The velocity function of galaxies in pure dark matter simulations is wrong. What I cannot show here because of rules of the Eagle collaboration is that when you actually put the results from the Eagle simulation, which is a cosmological simulation including baryons, then the line is a much better fit to the velocity function. Okay. So the structure of dark matter halos is affected by baryons as galaxies evolve through cosmic time. And that is a very nice and fundamental result from CALIFA. This is my final conclusion slide. I thank you very much for listening, and I'm happy to take questions.
Thanks very much, Jacob. Questions? Come on, questions? Okay.
Regarding the kinematical analysis and the estimation of circular velocity, you're trying to use as a proxy rotation velocity to circular velocity. You mentioned that you do some corrections.
Yes.
Do you do actually a model or just very basic corrections like asymmetric drift, or what did you do?
Mm-hmm.
And how much do you think this may affect? And also, if you have a control of the environment of the galaxies that you use to build this circular velocity function.
Okay. So the first question, We wanted it to be an observational paper, so we did not go do genes models and then get a circular velocity, which we could have done, but that would have been another paper. So what we did is we went to the literature, and there is a paper in which people have compared the measured circular velocity with something that comes out of a genes model. So effectively, we're kind of correcting for that. The asymmetric drift correction is sometimes very hard to do. If you have galaxies that have a falling profile, you probably know about this, then it becomes hard to do. So we try to find something that is more or less independent of this. The second question, I think, was about the environment, right? So we do have measures of environment, but CALIFA still has limited sample size, so environment is not something we have been dealing much with yet.
If you would like to compare with the prediction or simulations, you will have to take care of this.
Yes, you will have to take care of
Probably
this.
you are doing that already. But
This is the point about this, all this Eagle stuff, okay, so they make mock data, et cetera, but this takes time until it runs through, so.
okay.
When you estimate the circular velocity, you take in account no circular motions?
Yeah, this is related to the question before. So if you're a rotating disk and you had zero dispersion, then the circular velocity would be the same as the rotation velocity at a certain radius. But because there is dispersion in the z direction of the plane, the rotation velocity is a bit smaller. And we do a correction for this, yes, which is based on a literature average of galaxies of a certain rotation speed, dispersion, et cetera, but it's not a direct measure. It's not done for every galaxy. It's an average over a sample of galaxies. I realize I'm not being very clear here. If you're interested in the paper by Simona Beccarati, it will be all written down in detail, or come to me afterwards so that I can show you the plot where how the correction is done.
¿Más preguntas?
Lunch. Thank you.
Okay. Pues,
Mm-hmm.
We're going to have like a small drinks here.
Okay, great.